Thank you, Yui. Special thanks to you for inviting me to speak today. It's a little bit of a place of nervousness because of the place where we are. My first time I came to China to work on the China Central TV headquarters building back in the early 2000s, and we saw the state of construction at that time, and what we see today is nothing more than remarkable. What I'm about to show you today is a series of projects that we have been working on for the past 20 years, but we'll focus on the latest one. I'll talk mostly about this project in the end, but to get to this project, we have some other projects to discuss. It's really kind of a personal perspective. It's not to say that what I'm about to show you is the only way to do things or the way that things should be done, but rather a perspective on having gone through the ideas of construction. I'll start with a children's book. It's a book that I bought for my son many years ago when he was about 3 or 4 years old. And it's a book about Iggy the architect. And he was a little baby boy who was really into building things with anything that he can get his hands on. Outside, in the mud, inside, with food. But his teacher at school was not very happy with him going off on his own and building things in the classroom, because she had a little bit of a traumatic history when she was up in a high-rise building and she got stuck in an elevator. And this trauma had led her to have this anxiety against architecture, which was too much of the displeasure of this boy named Iggy. He was unhappy about this. One day the class goes on a trip, and they cross into a small island on a bridge. The bridge falls down. And Iggy, of course, comes into life and strikes up a plan and builds this bridge. And the teacher finds again the value of architecture. And this story really, by the way, my son is studying architecture at Hong Kong University right now. I had nothing to do with it. Over the years in America especially, there has been for a long time this kind of segregation between construction, making, and design, early design. And sometimes the architects are really involved in early design, conceiving with ideas, and then the construction happens later on with a different group of people. In an ideal scenario, these things become more intertwined, very much in a way that product industries operate, where things are much more vertically oriented, and then the whole thing is governed by a single entity. So this is an idea that really came about because I noticed that early in my career, designing part perhaps was easy, but construction was very difficult. This is where all the challenges come. And so there's a lot of kind of respect that I had developed for people that are in the industry of doing construction and making. And a little bit less for ourselves, where we thought we need to have a little bit more hand in making things a little bit more clear to the people that are making and building. We developed over 20 years, 24 years now, a process called PBIM and a thing called Elephant, which then goes into our process. You can also define it as something like virtual construction. where you build a building twice. You build it once in the digital world, and then you build it again in reality. Early on in my career, with this idea in my mind, we had an opportunity to test out this idea. It's a project that never got built, so it stayed in the kind of laboratory called SCL. It's a glass factory in Brisbane, Australia. It's a simple building. They wanted an office in front of their factory, which is the gray box in the back. And one of the core idea was to be able to utilize as much of the material coming from the glass factory to build this office in front of it. At the time, we were looking and searching for the right tools to be able to do this. And the idea was that, can design information be utilized for manufacturing? So it's a series of glass ribs, and we designed it in a way that you can manipulate things in a parametric way. And you can also do some visualization studies and also integrate engineering. But ultimately, we wanted to find a way to deliver a simple, dumb drawing that the factories could utilize for actual construction. Now, the power of this is that from the designer standpoint, let's say one of those bolt holes needed to move because of the engineering dictates that it needed to be further away from the edge. The drawings for these are thousands and thousands of sheets of drawings, and the corrections would take a long time. But if you did it correctly in the model, that these things could be done in a matter of minutes and not days. We did eventually get a chance to build something under this idea, a building designed by Lusail Tower, an LA architect for a project in New York. And it was kind of like the perfect situation where the developer was looking for some way to build his building in a different way. And I'm only talking about the facade, not the interior parts. It's a relatively small building, 13 stories tall, and clad with glass and stainless steel. And we wanted to think about how the building would get constructed first before we got into the details. Here are some parts and pieces that came from different parts of the world, including China. All of the glazing was manufactured here. And our modeling system, again, going from early design, utilizing that modeling system to deliver the manufacturing documents. And this was the very first panel that was made in a factory in Shenzhen and assembled. And one of the other things that we were really trying to achieve was to get the level of quality as high as possible in construction, and level of accuracy and precision, which we found to be very doable at that time. It was around 2006. The glass manufacturing was already very advanced by that time, but you can see that maybe some of the other manufacturers based in the United States would reject this project because it just didn't make any economic sense. The panels were then put into a specially designed crate on an open-top container and built in about a week. All of the facades went up very, very quickly because they were all made in these huge panels, and there was a very limited amount of site work involved. And in the end, these are some of the panel images of the stainless steel. We had to go down to Argentina to find a company that would make these panels for us. They were making auto body parts. These are kind of dies utilized for making fenders for cars. And it was actually the perfect shop get these panels made. And sometimes the paper and the digital doesn't really work because it doesn't really suit to the physics of reality. The first panels that were stamped didn't come out quite right because we had not accounted for spring-back nature of stainless steel. The dies were modified and also tried on mild steel. This looks like stainless steel, but this is mild steel. And it gives you this kind of very lovely form. In the end, those panels are also pre-insulated, weatherproofed, panelized. In New York City, the construction costs are very, very high. So this was also another way to do this in an economical way. So again, you can see a lot of detail here, very accurately and precisely put together for a project. And then after that, we had another opportunity to look at our process as a way to do a kind of an odd project for Kukje Gallery in Seoul with the architect Soil, who are dear friends of mine. The project is a small gallery, and it has these this kind of wrapper made out of stainless steel rings. It has a simple concrete box, and it has these appendages, the elevator shaft, the air conditioner, and the stairwell. And then the whole thing is sort of shrink wrapped with chainmail. Now, this is a material that we had never worked with before, so we needed to understand its behavior. You hang it one way, and it kind of droops down like this, and then you hang it 90 degrees in rotation, and you get a much nicer, happier chainmail fall. And we knew that that's the way to hang it onto the building. We also had to understand the kind of geometrical nature and behavior of the material, and we noted that the similar behavior between net and this chainmail. The first mock-up, I busted a lot of fingernails trying to make this out of key rings, and then to try to, again, understand its behavior. And then it all gets digitized. And that this is a relaxation model, because again, we are trying to mimic reality in the digital world. And what happens here is that once it gets mimicked with its kind of controlling points and its behavior, then can be analyzed and set to see what the state of this material is and what shape it forms when the chainmail is hanging on the building in its natural state. And then this is the kind of the mapping of its natural state. And we took that information and with the architects proceeded to build a 1 to 10 mock-up to see if the model was kind of true. And in fact, it worked out in a way that we proceeded to make the first chainmail mock-up itself. Those are not rips, these are just the seams which would be welded together with the rings. And then you have the digital on the left and the reality on the right. And it's not one-to-one exact, but we were confident enough to say, yes, the digital analysis does reflect reality. This is the first ring tested for load, and then trying to figure out how the rings would be made, which would be a series of coiled wire that would be cut. These are little parts and pieces that were designed to hold up the mesh. And then these are the terminations of the parts where they go into a channel to support the ring. And here you can see the first mock-up of the contraption at the top of the building where the mesh is hanging from. and on site. Now you can see that it's a little bit more complicated than it may need to be, but what we have here is that we wanted to prevent any concentration of load at the top edge where you would have the most amount of dead load and most amount of wind load. So in order to prevent the concentration, we added some springs that were daisy chained together at the face. So if you had any concentration, those would dissipate and be shared by the other connections. So then what you end up with is this kind of seamless wrapper around the building. And then we got onto bigger projects utilizing that methodology and that kind of thinking, pretty much in various different locations around the world. Morpheus is a project where we came on quite late, and the problem area was this middle part where you have the complex geometry cladding over the exoskeleton of the project. And we wanted to utilize our modeling to be able to document things very accurately, but in a very workable way in the field. We had to gather some information. We wanted to make sure that we have the architectural model, and then the structural model, which is onto the right, and then the orientation model, which is shown in the blue here. And that gave us the ability to understand what we needed to do between the structure and the cladding. As you can see, there's a lot of variation and empty space on the outer zones of between the cladding and the structure. And some metrics about what all of the parts and pieces, reaching a total number of 1.6 million parts, and of that, 1.2 million unique parts. So in some ways, there's no other way to do this rationally without going through a full, deep modeling process that was automated. But the design concept had to stay simple because we wanted each parts to be very simple that made the complexity in the end. So here you can see all those simple parts and pieces that were designed for this project. Any factory could make this. And then the assembled pieces, so that the factory could look at all of these parts and pieces that were assembled to see, visually check that they were in the right places. Now, every single part and piece in there is all tagged with a unique tag number so that it could be organized in the factory. Same thing for the sheets and all of the form work that is required to create the curvatures. I'll skip through this. This gets into a little bit too much detail, but it just basically shows, for example, how the process actually works. So we need to introduce some stiffeners, for example, in the back of the panel. We utilize the original model. We identify these bits first. These are the easiest bits, which are more or less kind of simply curved or straight. And then we identify where the brackets would be to hold up all of this and create the surfaces where the stiffeners would go. And once we try it out on a single panel and we know that it's going to work and its relationship to all of the beam location and the cleats, which are these guys, would then be all coordinated. And the magic here is really that all of that then gets automatically generated, and it's not somebody that's sitting there trying to model up all these pieces individually. We also need to do a check to see if it's correct. So all these self-address parts and pieces, we break it apart into individual parts and pieces and then bring them all back together to see that they do fall into the right location. The modeling also allows us to do mass engineering. When you have a complex building, often you might choose 1, 2, or 3 locations, which are the worst case, and design everything based on the worst case engineering. But in this case, we want to check everything and then create some sort of families or brackets that are going to give us a little bit more efficiency in the material use. So every single panel, every single condition then gets modeled through an algorithm and then output those results into a spreadsheet. And again, all of this is done in an automated manner. Output into including the locations of each cleat, which is that coordinated back to the main structure. And the structural steel manufacturer was really, really responsive and excellent to work with in receiving our digital information to be put onto their steel. And as you can see, they were located in a very precise and accurate way. All of the kind of attention, a lot of attention was paid to the brackets because, as you can see, the installation conditions are quite challenging. And it needed all the ways to install the panel in an accurate way, because if the brackets didn't allow you that flexibility, then the joints would be off. Now, if you take a flat panel and you try to align the panels, it's relatively easy, in and out, up and down, and you should be okay. But on a double curve panel, that adjustability is really, really key to getting the joints to line up. And as you can see, there's a kind of a tolerance of about 1 to 2 millimeters in the worst case scenario to create an alignment between the panels. The early modeling for the Lusail Towers project was very helpful in defining and knowing what the project is in terms of its size, scale, and quantities. And this is taking from the concept and doing early modeling for analysis to understand how much tonnage of steel or aluminum that you have, and other kinds of analysis to see how much we can reduce heat curve panels versus cold bent panels, so that in the end we're left with very few number of heat curve panels and majority of the panels going into cold bent. In the case of this project, doing mass analysis of the thermal properties of the facade in order to get to net zero passive house design accreditation. And this kind of early modeling and early knowing and unveiling what is sort of hidden in the project, I think is a key sort of idea for us. And whether it's solar studies like this, key issue that we wanted to ensure was that when you're driving down this highway, that the reflectivity from the building wasn't going to hinder the drivers on the highway. And then ultimately, again, looking for simple information for parts to be made for the facade. Now, the project really started in 2018, and we needed to be completed by winter of 22, which is the World Cup in Doha. So the process was really geared towards accomplishing that timeline. And again, in this scenario, we're involved in the concept design stage all the way through the manufacturing stage, which is this idea here. The building is overall geometry-wise quite simple. You have a cylinder that's been squashed at the bottom, rotated at the top, and squashed again. It looks like it's a little bit twisting, but it's actually the diagonal facade that's creating that illusion. Some indications of what the plan detail looks like. The top one is the long span, and the bottom one is at the ground floor lobby, and the bottom one is the typical floor-to-floor. You can see that as a modern glass tower, it's actually quite heavily insulated and shaded. I'm getting kind of an indication that we should come to a close soon, but I'll go a little bit faster. These are some earlier studies, again, to understand the window-to-wall ratio. These things must be defined much more earlier. And then going into machine intelligence on how to manage all of these variations. One of the things that we really worked hard to reduce was the heat bending, because it takes too long and it's too expensive. So we were able to get rid of 85% of the heat curve panels into cold bending. And in order to do that, we had to check to make sure that we could do that without compromising the seals and the IGU or the stresses in the glass. So of course you have to check the glass, you have to check the interlayer, the stresses in the interlayer, and the stresses at the spacer to do that. Ultimately, we started to analyze the panel itself and noticed that there was kind of a flattening here. And we wonder where that material was coming from. And it turns out that when you cold bend the glass as large as these are, you end up with a slight curvature at the edges of the glass. Now, a little bit is okay, but if you start to get a little bit, it might fall out of the pocket. And indeed, in the first panels that were made, we can see that the edges do curve in. These are the different conditions in the project. And so we came up with an equation to study this and put it into our algorithm that plots it out into a bounding box. And then check it again. Unroll it. This is kind of an interesting point where you cold bend the glass, and there's a kind of an inflection point here where it goes from one type of behavior and flips at this moment into another type of behavior. Physical samples were then scanned to see if our analysis is correct, and indeed it's giving us very similar characteristics. I'll skip through this because we're running out of time. Plot it again, and then ultimately the information really needed to just be checked against reality and then flattened for fabrication. The mullions also are kind of cold bent because, again, time constraints and costs. So we needed to see a way to make sure that these things are all compatible with the geometry of the building, but that we didn't have to go through the expense and the time to actually curve these panels or bend them or twist them. And so they were done all with the study so that in the factory, when they tighten up the corner screws, that they all fall into the geometry that it needs to be in. And so you can see the amount of cold bent pieces of glass in this project. And then that idea needs to then get spread out into mass fabrication automated systems so that it all can go into the factories either as a drawing or as a CNC code. This is for a different project, but the process is exactly the same. And then assembly drawings. I will be coming to a close. Thank you very much.